Welcome to the Explainer. Today, we are taking a high-altitude approach to one of the most notoriously challenging topics in the entire Cambridge 9618 computer science syllabus. We are talking about implementing linked lists using arrays. Think of this as your advanced aerial combat tactics for exam day. We're going to break down the exact step-by-step strategies that separate the okay answers from the absolutely outstanding ones. If you've ever felt like you're flying blind when tackling complex data structure questions in Paper 2 or Paper 4, you are in the right place. We are going to lock onto the target, decode the examiner's radar, and give you the ultimate flight manual for scoring top marks. Let's get right into it.
So let's dive into this crucial question that every single student asks. What actually separates a B from an A star when you are asked to implement linked lists using arrays? To understand this, I want you to imagine two different computer science students taking the exact same exam. We'll call them Alex and Sam. When confronted with a massive 15-mark question about array-based linked lists, Alex panics and completely overloads the page. Alex dumps every single raw computer science fact they've ever memorized about nodes and pointers, but provides absolutely zero analysis. It's just a wall of text. Then you have Sam. Sam is watching the clock, rushing frantically, and completely misses the specific command word requirements in the prompt. Sam just writes a few bullet points and draws a messy diagram. When the examiner's red pen comes out, both Alex and Sam lose massive points. The difference between them and an A-star student isn't just about having an encyclopedic memory. It's about mastering exactly what the Cambridge principal examiners are looking for in your logic, your structure, and your overall approach to problem solving. We are opening up the examiner's playbook today to decode the precise roadmap that guarantees top marks.
Here is our flight plan for today's mission. First up, we'll cover the core theoretical foundations. Second, we'll walk through the technical methodology. Third, we'll look at evaluating algorithm quality. And finally, we'll finish strong with the top examiner warnings. We're going to transform those red pen marks into green check marks.
Let's clear the runway and start with Part 1, Core Theoretical Foundations.
We need to start by building the conceptual scaffolding, because isolated knowledge simply won't survive the toughest exam questions. Now, what's really interesting here is a major examiner alert. Principal examiner reports reveal that candidates consistently confuse key terminology. You cannot afford to lose marks before you've even started coding or analyzing. This is where we introduce the PEAL framework: point, evidence, explanation, and link. Top students use this to structure their extended responses perfectly. When you are writing an answer, your point should explicitly define the elements of your linked list, like the data array and the pointer array. Your evidence is defining the head pointer and the free list pointer. Your explanation details exactly how the index of the array acts as the memory address, and your link ties it back to the specific scenario in the question. Defining your terms up front using this framework anchors your entire answer correctly. It tells the examiner, I know exactly what these command words mean and I know how to apply them.
The dividing line between average candidates, like our friend Alex, and top-tier candidates comes down to this connected conceptual understanding. The syllabus heavily emphasizes that top-performing students don't just rely on rote, isolated knowledge. They exhibit cross-topic integration. For example, an average candidate might just say, arrays store data. But an A-star candidate, they connect it. They explain how implementing a linked list within a static array impacts overall memory management. They understand that since the array size is fixed at compile time, we have to manually manage a free list pointer to track empty slots. Let's do a quick mental challenge right now. If I say a linked list uses two one-dimensional arrays to mimic dynamic memory allocation, is that an Alex answer, a Sam answer, or a PEAL-structured top candidate answer? If you guess top candidate, you are spot on. Demonstrating these causal relationships and successfully transferring principles to completely unfamiliar contexts is the true hallmark of an A-star student.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Awesome. Let's keep climbing. Moving into our second maneuver, the technical methodology. Now let's move into the practical application and initiate the transformation. We are shining a massive spotlight on what we call the method mark strategy. This is where you earn vital points simply for your process. This is the computer science success blueprint in action. Algorithmic thinking requires a highly standardized sequence. Step 1 is step-by-step decomposition. If you have to insert a new node, what do you do first? You check if the free list pointer is null, right? Because if it is, the array is full. Step 2 is data structure selection, justifying why an array-based linked list is the right tool for the job. Step 3 is efficient code implementation using clear pseudocode notation. And Step 4 is rigorous testing. Imagine a timer going for 60 seconds right now. If you were forced to write the logic for deleting a node, could you do it? You'd have to update the previous node's pointer to bypass the deleted node, and then link the deleted node back to the free list. Algorithmic thinking is systematically awarded marks when you follow this sequence and show clear logical working on your exam paper.
Let's see how this blueprint builds into data interpretation. Sometimes Cambridge throws a massive curveball and gives you memory dumps or complex binary representations of an array state. Interpreting these is notoriously difficult. But look at this sequence. First, you systematically extract the data from the binary or hexadecimal representations. Don't panic, just decode it. Next, you perform your calculations to figure out where the pointers are actually leading. And finally, you draw evidence-based conclusions about the state of the linked list. Is it traversing correctly? Is there a loop? Here is the absolute key takeaway. Even if your final calculation or conclusion is slightly off, extracting that data logically and showing your step-by-step decoding is where you secure those critical method marks. Those method marks act as your parachute